morning, everyone. I warmly welcome you all to today's session of our faculty development program on quantum computing. We are glad to have such an enthusiastic participation as we begin this exciting journey into one of the most promising fields of technology. I would now like to introduce our chief guest, Dr. Aswath Babu sir, Assistant Professor in Physics, IIIT Dharwad, Karnataka. He is a physicist and quantum computing researcher with interdisciplinary expertise in quantum natural language processing, quantum machine learning, and quantum internet stimulations. He has established a strong research foothold in quantum optics, nonlinear dynamics, and quantum information theory with an interdisciplinary span into quantum computing and application-driven quantum stimulation. Following PhD studies on nonlinear dynamics in optical systems, he has advanced to postdoctoral roles at IIT Madras and London University, highlighting the solid foundation in both experimental and theoretical forms. He has delivered 9 expert lectures on differential equations, numerical solving techniques, delivered 10 expert lectures on statistical physics for quantum computing, quantum sensing methods, and applications. He has hosted IBM Quastic Fall Fest from 18th to 20th October 2024 introductory section led by expert IBM speakers providing insights into the fascinating world of quantum computing, followed by a hackathon on the final day offering participants an opportunity to hallow their skills and compete for exciting IBM Squad prizes. Conducted workshops on future of quantum information processing on 15th June 2024 at IIIT Dharwad. Welcome once again and let's get ready to quantum deep into the future. Now I hand over the session to Dr. Aswath Babu sir to enlighten the crowd with his valuable expertise and knowledge.
Thank you very Thank you very much, Sam, for a very deep and brief introduction of me. Once again, very good morning to all the participants. Hope you had a nice breakfast and be ready to start getting into the domains of quantum computing. So first and foremost, I would like to sincerely express my gratitude to just a minute. First and foremost, let me ask the participants, are you able to hear me? You
Yes,
can
sir,
just...
yes, sir.
Yes, sir.
Yes, sir. Yes, sir. You are here.
Great. Thank you. I think somebody was posting WhatsApp on the chat messages that they are here after joining FTP, MNIT FTP. Yeah, good to see you here. Right. So I would like to thank the organizers, first of all, for giving me the opportunity so to talk to you people with this introduction. Okay, right? That's one thing I would like to sincerely thank. And it's an invaluable opportunity for me to get to interact with the people and also share the understanding what I have gathered so far on quantum computing. So I hope that this is a first session or something like that. So I would try my very best to give some the base, like initial essence of this quantum computing. With this, you can launch into the field. Okay. And if you already have some knowledge about this, whatever I'm going to discuss, please treat it as some kind of a revision. Okay, right? So let me check with the organizers. You wanted to record the session, or it is just like that? If you wanted to record the session, you can go ahead. I have no objection for recording the session.
Yes, sir. Actually, more than 100 participants registered, so that we are giving live streaming in YouTube, sir.
Okay. I think it will be recorded there, I guess. Okay, fine. Okay then. Yeah. So we have about, ma'am, how much time do I have? 2 hours, till 12 o'clock, or I have to stop at 11:30?
Yes, sir. 12 o'clock, sir.
12 o'clock. Okay, we have sufficient. 2 hours. Okay, great. So we have sufficient time, so we can go slow. right? So I would try my very best to introduce the topic, and I will go slow. I have my PPT here. What you are seeing is my PPT. Okay, and what I will also do, I'll use my like a onboard or a hand notes, something like this. Okay, so I will be using my hand notes and explaining the things. Let's say quantum computing introduction. Okay, right? So I'll try to use this as much as possible so that it is more interactive, not just listening to some kind of a show. Okay, right? So that is what I would do. Right. So let's go straight away into the business. Okay. Let me go to the first slide. What I have here. Okay. So what you can see here, this is a person by name Richard Feynman. Probably people have heard about him. Okay. Or if you have not heard about him, please know by now. Okay. So in a way, he is actually one of the greatest physicists, and more than that, he is known for his teachings, like the way he teaches his course. Right? He is very good in teaching fundamental physics, and he introduced the fundamental physics in very subtle or a very simple manner, so that the even common people, those who are having no background in physics, can understand. So he would to usually take a real world example and teach the fundamental topics of physics to the students. So looking at those lectures, some of his students thought it's a very interesting way of understanding physics and more knowledgeable way of understanding physics. Okay, and they started collecting all his tutorial like a lecture notes and published in the name of Richard Feynman lectures. Okay, so they are going to like they have become very famous. In a way, it is actually used. These lectures were used as a preliminary understanding for competitive exams like JEE or other master's level exams even too. Okay, so that is how he was known for us from the physics domain. But he is actually should be said as the father of quantum computing. Okay, why he has to be said as a quantum computing? Because back then in 1960s and before, okay, so quantum computing actually is based on quantum physics. Okay, so what happened? Okay, quantum physics. Okay, the born like a birth of quantum physics happened between 1900 to 1925. So the reason is because the people were unable to explain few few properties at quantum level. At quantum level, okay, quantum level in the sense atomic level. So from there, 19 before 1900, some experiments like black body radiation, okay, and people were studying black body radiation and atomic spectra of gas. So you burn the gas, what you see, okay, and the stability of the atoms, you can say, stability of the atoms. I'll just give what I mean by this. So these are the main three experiments which led to quantum physics birth. Okay, why I'm bringing this? Because unless you don't know why quantum physics born, you would not appreciate what is quantum computing on which it is being built. Okay, so a very simple example I'll bring here: stability of the atom. Let's take an atom with a nucleus. Let's take a valency orbit with an electron revolving around. Okay, right? As we know, electron revolves around, it makes oscillation or rotation about the nucleus. Now the question is why the electron is not losing the energy? Not losing the energy. It is fair question to ask. Okay, because if somebody runs in a circle forever, he should lose some energy, right? Okay, but the question is why it is not losing the energy. Moreover, there is a force of attraction between nucleus to the electron. The Coulombic force of attraction is there. Coulombic force of attraction. It is there. Why the electron is not giving up, losing energy and falling into the nucleus because of the force of attraction? That was the question asked, and that is the reason, like one of the main reason. Okay, so why electrons are not losing? Because of that, the stability of atoms are coming into the picture. Okay, so the stability is coming, and by default, nature has given that stability. Okay, nature has given the stability to the atoms. Okay, right? So because of that, the things are stable. Now the question is, the experimentalists were asking the theoreticians why the atoms are staying stable. Okay, we understand nature has given that ability, and why the things are remaining sustained without losing energy when they are rotating about a nucleus. So that is the time the Bohr came and Bohr gave his model. The answer is Bohr model of atom, Bohr atomic model. Okay, right? And the next thing is the other two experiments like atomic spectra. For example, if you take a gas inside a box, okay, and you burn it and take a small hole and take out the what is the light coming out from that particular gas, okay, what you see is the spectrum for particular frequency. I have such particular peaks. Okay, I'll have few peaks here and there. Okay, atomic spectra. This is the for frequency omega 1, frequency omega 2, I have peaks. Okay, so these peaks like energy of the, let's say energy density, you can say energy density at particular peak there is some value, and it is not a continuous spectrum, means the intensity of the light is not coming from all the frequencies. As if you burn the gas, you see few colors. Let's say a green color you see. Let's say you see yellow color. Okay, only a few colors like a sparks you see. But if I fill them, like if I take a metal, you burn it, means heat it, what you see is continuous spectra. Okay, it is actually called block body radiation. Block body radiation. Okay, right? For all the frequencies, I have some energy density, particular energy density. Okay, the question was asked. Now we know that it is a metal and it's a gas. Because of that, the difference may be there. But back then, people were not understanding because the quantum physics was not born. So to answer these questions, Planck, okay, a physicist by name Planck, he came and he gave the energy spectra. Means energy always comes in the form of photons. The radiation, okay, right? Radiation comes in the form of photons. So the moment you introduce the idea of energy in the form of particles, okay, right? So energy flow in the form of particles. What are the particles? Which are photons. Okay, everything falls into the picture. The moment you introduce that, okay, everything, let's say people are able to explain while the atoms are stable. The answer is the atoms are stable because the angular momentum with which they are rotating in the orbit is conserved. Means it is not going to lose any angular momentum. Angular momentum is, okay, linear momentum is just the mass into velocity. Angular momentum, okay, let me write down what I mean. Okay, angular momentum is actually r cross mass into velocity. So this is the linear momentum. Okay, so this quantity is actually conserved, means it is not going to change, not going to lose any velocity as the electron revolves around the nucleus. So that velocity always remains the same. Because of that, the kinetic energy of the electron remains the same in that orbit. So kinetic energy is conserved, so it never loses the energy. It remains in that orbit forever. Okay, so that is the one of the reason. And one more reason, let's say it is trying to lose the energy. Let's say electron is losing the energy, means it is falling from outermost orbit to lowermost orbit. Means whatever energy difference between outermost orbit to lowermost orbit comes out as some energy or a radiation or photons. So that is when only it loses the momentum. If it is losing a momentum, is nothing but it is going from one orbit to other orbit. Okay, right? So we should not deviate too much. And why I am bringing this, because you should understand the idea of the photons, the idea of electron existing in various orbits. So to bring that idea, I brought these things here. Okay, now Planck came and other people like Schrodinger, Dirac. Okay, all those people, okay, Schrodinger and Dirac, okay, Paul Dirac and others, even Einstein. Okay, so they contributed, okay, contributed for the birth of quantum physics, for quantum physics. Okay, so it was nicely poised till 1925. The quantum physics was superb. It was able to explain things happens at a quantum level. Now the question is, okay, people were happy till 1940 or 1950, and some people wanted to understand, for example, so around 1950s, let's say, let me take a simple number, the time, they want to understand photosynthesis. Okay, so what is photosynthesis is, if you just take a plant, okay, right, it takes the sunlight and takes the minerals from the ground, okay, minerals, it converts that into required energy to the plant with very good efficiency. Photosynthesis, a very good efficiency, okay, with very good efficiency, the, okay, very good efficiency is shown by plants. Okay, so we were like, people were trying to mimic or replicate back then using, okay, replication using photovoltaic cells, photo or solar. Okay, but it was not possible because that high efficiency, very close to 100% efficiency, we were not able to reach. So people started understanding what happens at very small quantum level, how the plants were able to execute such a very good efficiency, as if they know to go to that 100% efficiency in no time, without losing any time, no delay. Okay, so people were trying to understand why the photosynthesis is happening. By the way, photosynthesis is biochemical process. Okay, chemical process happens at quantum level. Okay, And when they were trying to understand, okay, understanding, there are so many factors involved. So many factors. Let's say there is, let's say I want to further invest on a stock market, right? I want to pick the best stock to invest. There are so many factors involved. To understand all those factors, I would have to put a lot of effort understanding them. So understand whether this factor influences, in that case, or there is another factor. So likewise, there are so many biochemical processes or features which are actually influencing this photosynthesis. To understand that, you need a mathematical model. Okay, one needs a mathematical model. A mathematical model or any model you say, right? Understanding mathematical is required. Problem with this is you can't do it on a paper. You need a computer. So back then the classical computers were there, and there were so many factors. The classical memory, whatever classical memory has, okay. So classical computers means conventional computers. I mean classical in the sense computers, memory, and processing capacity, memory and processing capacity was very limited. Okay, and people were struggling to process or model that perfectly using the quantum classical computing. Okay, so that is the time this guy came, this person, the greatest physicist. In 1959 itself, he sparked the idea of you better devise a computer or a machine based on quantum effects, not a classical effects. I'll tell you what is a classical effect in a later slides. So in a way, he just hinted, and later on he gave a full-fledged lecture, okay, and then published the work related to that. Okay, so the essence is you better devise or design a classical computer or a machine which is based on classic quantum physics rules, not based on quantum physics, classical physics. Okay, so classical physics is a macroscopic world, real world where we can see things in, let's say, if I have a mouse, I can touch and feel that. But if I have a small entity like an atom, I can't touch and feel. It is so tiny. Even I can't see with my naked eye. I need a advanced equipment to see that. Powerful scanning, tunneling microscopes, or so on to see things at the atomic level. So he just designed. He just said, you better come up with such a quantum computer or a machine based on quantum physics rules. Okay, fine, very good. So people understood. Okay, so we have to follow, or we have to continue the idea which the sparked by Richard Feynman, and his famous quote is there on the right, which is like many times people have repeated. I don't want to repeat again, but I'll just tell the essence. Like, you better come up with a quantum mechanical based machine. Okay, so right, following with this talk, okay, this person named by name David Deutsch, okay, he took the idea in 1995. He actually came up with a universal quantum computer. Okay, it is named like that or coined like that, but what it is simply based is, it is simply based on two-state system. Okay, what I mean by two-state system is, you just to take a simple example. Okay, right? Okay, in 1985, David Deutsch. Okay, Deutsch. Okay, what he did, he took two-state system. Two-state system. Okay, the simplest example, simplest classical analog for us is, classical analog means something just behaves like that in a classical real world, is a coin, just a coin whose toss and heads are there. To take a coin, toss a coin. It will have the states of both the natures. What is that? Both the natures is it will have head form sometime, tail form sometime. So basically, it is flipping between head and tail continuously. Okay. So during the flight I am talking about, the system is existing in both the head and tail form. So such systems he took, and he taken such systems. Anyway, he did it with theoretical modeling. So he has a freedom to choose anything. He just took two theoretical models, okay, the two systems. Probably they may have a possibility to interact with each other, influence with each other. And he took such two systems or multiple systems, and he came up with a universal quantum computer, or a machine or a calculator which does a very basic level operations, like say adding few things. Okay, two state systems, okay, leads to a machine, a computing device which could do few operations. Few operations. Okay, remember, it all starts with those few operations. Later on, you can go for the advanced level of like new system. Okay, so David Deutsch did that. Okay, it's very good, and it is called a universal quantum computer because the idea was to use that machine for any calculation. We should not confine ourselves to a particular case. That's why it has to be used for any case. Okay, so the model two-state system was there, and he showed such a quantum machine could simulate any physical system much faster than classical computer. It is a very good result back then. Means if I want to mimic any mimic any physical system, right, which have like involve some quantum physics changes, if that changes has to be modeled or mimicked or replicated on a computer, so that classical computers were existing then, they would take some time to show that same modeling or same process on the computer. But his David Deutsch universal quantum computer can able to perform or execute the same mimicking in much quicker. So that is a very positive step for initial quantum computing growth. Okay. So next came, and there is one more physicist or plus mathematician. Okay, his name is David Deutsch. Sorry, his name is Richard Joyce. Okay, Richard Joyce. He came and he joined with David Deutsch, and said, let's design a set of codes or steps to use this universal quantum computer in more effective manner so that we could execute some useful tasks. So basically, they came up with set of steps required to execute a particular useful task. Let's say they call it as a David Deutsch algorithm, or a quantum algorithm which could be implemented on that universal quantum computer designed by David Deutsch earlier. Okay, so the quantum algorithm started with that. Okay, so in fact, we would start tomorrow the David Deutsch algorithm and Deutsch Joyce algorithm. Before that, we will touch little bit about there is something called quantum teleportation, quantum parallelism. Okay, basically these things led to the advanced quantum algorithms like Shor and Grover that we will see in the later slides. Okay, so very good. The formulation of quantum algorithms taken place in 1992 after 1985 Dutch universal quantum computer. In 1993, later on, Chils and Vajrani, these are the two people, Umesh Vajrani and Ethan Bernstein, they showed this quantum algorithm with a quantum on a quantum computer could be significantly very faster than classical computers, the Dutch already seen that. And what this Umesh Vajrani and Bernstein actually proved is, even when you allow the classical computers have some probability of errors, okay, so there is a flexibility given for classical computers, okay, so that flexibility is given. Even that flexibility is given, they may take some time to execute a particular task. That much time is surpassed by the quantum computers. It is just like the additional advantage given for classical computers. Even then, the quantum computers were able to outplay the classical computers in a greater manner. So in that way, it's a significant fast, right? So one can say it's a very good positive direction the quantum computing research was going in that time. Okay, right? So even Bernstein's Vajrani algorithm is just like finding a number from data in much fast than the existing classical algorithm. So that is what Bernstein's Vajrani algorithm. Maybe tomorrow we'll just slightly touch what is that algorithm is all about. Okay, right? So yeah, now after that in 1994, so the crown jewel of quantum algorithms actually given by this person is mathematics physicist. His name is Peter Shor. Okay, so you might have heard about him in terms of the quantum computing. Oh, like is going to attack this RSA encryption in a coming days. What is this RSA encryption is? Okay, let me use my quick hand note. Okay, so existing security, okay, existing cyber security, let me call, or internet security is based on RSA encryption. Okay, so what is that is our passcodes which are publicly available outside, okay, means even though we secure our passcodes with our name, we secure, anybody can try that passcodes, right? They can guess the passcodes. So it's like a public key, okay? So which were actually the factors of a very large prime number, or we can say they're connected to very large prime number, okay? So the P and Q, let's say, are the factors of very large prime number, okay, right? Very large prime number, and PQ are the ones which helps us to create a key or password. Okay, now the question is why anybody can't pick the P and Q randomly, because as of now when you try to log into your internet account or SBI or any Canara Bank or any bank account, if you make 3 attempts wrong, your account is going to be blocked, which means if some imposter is trying to crack your password, he is only allowed to do it in 2 shots. In 2 shots, guessing this particular P and Q is not going to be easy. Okay, right? Existing with the encryption number of bits encryption level. Okay, so guessing this P and Q in 2 shots is impossible, right? It may require more than 3 or 4. That's why the banks have put as of now within 3 attempts. Okay, it will close. If you take every 2 days, like every day twice 2 attempts you can make, it would require about 30 days to crack any given password. That's why banks are telling you please change your password within 30 days. Okay, so by the time some imposter tried some 29 days, he exhausted all the required passwords. On 30th day he may crack your password that you are going to change. So in that way you are going to secure your account. That's why banks are doing it. Okay, but the actual background or behind the scenes things is the large prime factors are the large prime number and whose factors we wanted to find. Okay, so existing technology, or even if you use a powerful GPUs, it will not be able to find P and Q within 30 days with the 2 attempts in a given day, right? So, but the question is, if Peter Shore's algorithm, if you use, okay, if you use Peter Shore's algorithm, you can crack this password, okay, Peter Shore's algorithm, you can crack this password or find this P and Q, okay, okay, you can find P and Q for given N in one shot, okay, you can find for a given N in one shot. That is a commandable thing, okay, and it's a commandable. At the same time, it is dangerous for us because our security is going to be vulnerable. Means somebody who is having a quantum computer who could implement a Shor's algorithm on that, he can crack your password in one shot. Okay, so that is the problem. That's why everybody wanted to understand what is quantum computing. Everybody wants to come up with a new encryption technique which is resilient to this Peter Shor's algorithm. Okay, so that is what people were trying to come up with, post quantum cryptography. Okay, post quantum cryptography. Okay, I'm a bit fast. I want to write short, but I will not able to write short. So that's why this little bit of overwriting. Let me rewrite post quantum cryptography. Okay, so basically they were taking into consideration, even with Peter Shore's algorithm, how can we secure our classical communication? That was the idea. Okay, right? So in fact, this Peter Shore's algorithm would require a quantum computer. Okay, right now require a quantum computer with something called 10,000 qubits. Okay, right now people are hearing for the first time what is a qubit. You can take it as some kind of a memory size, some kind of a processing ability. Okay, right? We'll come to that, what is this qubits, in a later slides. All right, okay, so let me go further and use my presentation. Okay, so Peter Shore came up with his algorithm, very powerful algorithm, which is going to affect or create an impact on the RSA existing encryption technique. Okay, so another crown jewel of quantum algorithm given by this person is named Low Grover. 1996 he gave an algorithm, very powerful algorithm. What is this algorithm is all about is, if you have a data which is unstructured, you can find the element out of that data in much quicker fashion than any existing classical algorithm. That is something very interesting. You see, let's say some students are sitting in a classroom in an increasing or a decreasing of roll number. If you want to pick a particular student with a roll number, certain number, you can go immediately to that person and you can pick. It's very easy. Okay, if they're sat in if they're sat in mixed order, unstructured order, without asking them, if you want to pick, okay, without announcing in overall louder, you want to pick, you have to go and ask each person, are you such and so roll number person? Are you so? So you would need certain number of attempts and you would take some time. You would be taking some time. But Low Grover came up with an algorithm which can give you such capability among unstructured data in a quadratic speedup. Okay, let's say if the data size is some n, right? On your worst day, let's say there are 100 students are there. You want to pick a certain student with a particular roll number. On your worst day, what happens? You would need all the 100 steps, because the last, you would be searching for the person who at the last. Okay, so let's say n data size is there. So to pick an element, okay, pick an element from there, you would need n steps. That is the worst scenario. We have to take that scenario also into the picture. Okay, but he said, never mind, I'll give you an algorithm which can be executed on a quantum computer, where you could pick that element from that unstructured data. Remember, the data is not structured anymore. You can find in just say square root of n steps, right? From n to reduction to the square root of n is amazing. Okay, so the Grover's algorithm in fact led to so much of optimization techniques, right? So it's like a foundation for many quantum algorithms, because it deals with the unstructured data. Remember, every computation is nothing but searching something from a data. Even if you are talking about multiplying 2 into 3 is equal to 6, it is searching for a 6 which is equivalent to 2 into 3. Okay, 2 into 3 means what for me? 2 into 3 is adding 2 3 times. Let's have a couple of books. Such books, if I have 3 times, how many books I am going to have? So that is overall 6. So how do I find? I would be counting and searching for this 6 out of the number system. So it is all about finding some functional value. So in that way, Grover came up an idea or its algorithm where things can be much faster compared to classical algorithm. Okay, so that is amazing thing Lord Grover did. And in 1996, you see, the Seth Lloyd, biophysicist, okay, right? He finally achieved the main objective of the birth of quantum computing. What was that? Is he is able to mimic or simulate a quantum mechanical systems, okay, using this quantum hardware or a quantum computer. Okay, so in fact, this has many implications like a drug design, because they were able to understand how things happen at a biological level, a quantum level. Okay, even at a material science, how things will combine to create a material, right? And high energy physics applications also led or born out of this simulations. So he was able to explain using quantum computer why, for example, why the photosynthesis is like that. Okay, right? If you just take a caffeine, if you just take a coffee, right? There is a caffeine molecule which dissolves in our body, and how it gives some kind of extra energy, like high energy, to a person immediately, right? To understand this, it is impossible using existing classical computers. Even if you use a supercomputer, still there are so many electrons involved in this caffeine molecule. So those things are coming into the play. So understanding the effect of them to the, let's say, going and interacting with the protein molecule in the body. Okay, so that's very complicated biology. Okay, so he was initially, the Seth Lloyd came up with simulation of quantum mechanical system. Okay, right? So the objective was realized around 1996. Then, if you just see overall the growth of quantum computing from 1980s onwards, from the Richard Feynman full-fledged lecture onwards, you see initially there was growth is very steep, very flat. Later it picked, and as of now, if you see in the last 10-15 years, it's a very good growth, which almost straight line. It is trying to reach a straight line in the quantum research sense. Okay, it's a very promising for our understanding, or let's say there is so much of material is being came up, so much advancements in the technology, right? Initially in 1980s, people were asking, you are talking about quantum two-state system, like a quantum coin, realizing that quantum coin is so fragile, right? It's fragile means it gets affected by the surroundings around temperature. So it's difficult. It's difficult to realize a computer, that state system, two-state system. Forget about calculations like that. People were talking later in after 1990s. People are able to realize quantum, this two-state system. We will be calling it as a qubit. We'll come to that. What is a qubit in the later slides? Okay, so the technology advanced, the theory got advanced, the understanding got advanced, and the quantum computing got into the groove, and it is on the right track by 2010s. Okay, so let's go further. Let's try to understand how this two-state system is going to store some information. Okay, it's a memory. Okay, first of all, to understand that quantum memory, we want to build on a classical information or a information which we already know. We are already using classical computers where the information is stored in terms of bits, zeros and ones. Just for the sake of the people who are not having a background in physics, for them, I'll just bring a little bit of physics here. If you just take a new atom, a nucleus is there, there are electrons around. The only matter, the electron which matters for me is the valence electron, outermost electron, which is there in the all the way outermost orbit. If the electron, if you notice, it is revolving around the nucleus, we already established that. That electron revolving around, in fact, it acts like a current carrier in that wire, which is in a circular manner, it is wound. So orbit of an electron is just like a wire or a DC current carrying wire. DC, direct current carrying wire. Okay, as we know, if you have, okay, as we know, as per the Maxwell's equation or Biot-Savart's law, there is a magnetic electrostatics and magnetostatics is there. So if I have a positive charge, it generates electric field around. Okay, electric field lines. What is this field lines is? If there is a negative charge, small negative charge around, it will be attracted towards that. If there is a positive charge around, small positive charge, it is repelled from that charge. Okay, so that is what these field lines are about for a nucleus, sorry, for a positive charge. Negative charges are attracted towards this positive charge, or any small positive test charge is there, okay, that is repelled. So that is what the field lines are actually showed. Now, if the charges are stable, there is a field lines are straight. Okay, let's say charges are moving in a straight line through a wire. Let's say positive charges are moving. Okay, they are moving. In that case, what happens? The field lines of this electric charges will curve around. Means they're no more straight lines. They curve a little bit. So when they curve around, what happens? There is a curling of electric field lines happens. That is represented by mathematical symbol. Curling of electric field line. Del cross E is a curl of electric field line, is going to give you some rate of changed magnetic field generation. Okay, so the curling of electric field lines behaves like a source for magnetic field. So the magnetic field is generated out of this current carrying wire in a circular fashion. Okay, so if I have a thumb showing the magnetic field direction, sorry, electric field movement and the charge movement, the curling finger would show the magnetic field generation. Okay, so that's why a DC current carrying wire, a direct current carrying wire would generate a magnetic field around the wire in particular clockwise or anti-clockwise depending on the current direction. So there is a current, there is a magnetic field generated about that current carrying wire. Now if I just take the wire, take the current carrying DC current carrying wire, wind it into a circular fashion like a ring you create, Now the current goes through a ring. Now question is how the magnetic field is going to behave. Now the magnetic field is going to behave as a rings everywhere, right? So interestingly, the magnetic field strength gets added in the center of the ring or the inside the ring. It is going to cancel outside. Because of that, electric magnetic field lines cancel out. So inside there is a magnetic field add up. So the magnetic field strength would increase just like this. So the magnetic field lines comes out like this. So if you notice this magnetic field lines of a current carrying wire, okay, so because of this, it acts like the current carrying loop acts like a bar magnet, like a north and south pole. Okay, so the magnetic field lines, if you see, they are like this. The north pole electric magnetic field lines exit, in the south pole they enter. Even if you just see the magnetic field of Earth, you see there is a butterfly kind of effect on one side. On the other side, you see magnetic field lines are no more connected because of that. Because why it is not connected? Because of the solar flares coming from the sun. There was so much of solar flare, so much of solar energy coming that is actually impacting the magnetic field lines of the Earth. Okay, you forget about right now. Now, if you see current carrying loop or a orbit of an electron is just like a magnet or a small bar magnet. That is what established here. So what people do is people take a small bar magnets or such thing and arrange them in a particular direction. Let's say a magnetic strip. Let's say a material made up of some conductor, right? If you just take that magnetic strip, if you notice behind your credit card or a debit card, there is a magnetic strip behind. So that magnetic strip is actually made up of a small thin film, okay, where there is a material where there is a each atom would create a small bar magnet, okay, right? So so that such bar magnet is there. I arrange the bar magnet in that strip, or let's say there is few thousands of bar magnets. Arrange them all from north to south, arrange left. So I call them as 0 bit. If you arrange in the opposite fashion, south, north, you call it as 1. Okay, so in this way you can store the information on the magnetic strip in the form of zeros and ones. So one information here is you would be needing few billions of atoms to store 1 bit. And remember, it is deterministic, means all the atoms were strictly arranged in a left to right fashion in their magnetic movement. Okay, so this is how you can store the information. If you want to retrieve the information, you can use some magnetic sensor where depending on how the magnetic field lines were arranged or magnetic dipoles were arranged, accordingly you can find what is the data being stored there. Okay, fine. If you want to increase the amount of storage, you can do lateral instead of going a straight fashion. You can store the information in a horizontal fashion towards the flow of the tape. Okay, so you can retrieve the information. This is a classical information for you, where the information is stored in the form of bits 0 and 1 that we know already. Now we got to know the physics out of it. Okay, now what is so different about quantum computing? Is it something like this? What is quantum memory? Is something like this? That is what we want to find out. Okay, now as we know, right? Okay, so atom means there is a nucleus. There is a nucleus is there, right? So about the nucleus, there are orbits around the nucleus. There is an electron revolves around the nucleus. If there is some energy provided to the nucleus or electron, it is tied up with the Coulombic force of attraction to the nucleus, right? So it is just like some thread is there. If some thread is stretchable, I can stretch that to a larger distance. So I need to exert some energy. So here in this case, so atoms are so tiny, electrons are so tiny. If I send a photon of energy h mu, that energy is exactly equal to the separation between any two levels of an atom and electron orbits. In that case, what happens? Electron has a chance to observe that photon, go out into the outermost orbit. Okay, so that is what usually we think in a classical way. If I supply energy to somebody, he would take and consume that energy. Let's say I give some food. Somebody is hungry, they will eat it. Okay, somebody doesn't know hungry, they may say they not eat it, they will say later they will eat it. Okay, but when it comes to electron, if you supply a photon, right, even though it is hungry, it is capable of eating. Sometimes it absorbs, it comes out to the new orbit, outermost orbit. Sometimes it doesn't. Sometimes it just stays. So when it stays, the photon just get exited without being noticed by this electron. So this is a strange thing for us in a real world, right? So what is the strange in real world is, if I perform this experiment like 100 times, let's say 40 times the electron is not observed, okay, and 60 times the electron get observed, percentage wise I'm writing, which means there is a probability or there is a chance involved in this case. It is just like I give something, some food to somebody, somebody eats it with 60% chance, and 40% chance they just throw it away, something like that. So in a classical world, it's difficult for us to understand because we are wired to understand the classical way of thinking. Okay, but at a quantum level, this is what happens. Things are not certain, things are not fixed, things are not deterministic, things are ambiguous, means confusing. What is that confusion is? Sometimes it absorbs, sometimes it doesn't. The only way to express that effectively, only way to put that onto paper, I have to bring the idea of probability. So that is what the probabilistic excitation. I just put the slide name. Okay. So when I supply energy to a photon, so energy of photon to an electron in an orbit, it might jump to the outermost orbit by taking that energy, or may not. It will just stay in the same orbit, and the energy supplied is just comes out as it is. Okay. Now people thought that very fine. Okay. So there is some process may take place here. Can we use that probabilistic excitation as a means to realize a memory out of it? Right? So because it's a quantum process, by the way, if I can realize a memory, I can process the memory and I can do some quantum computing out of it. Now the question is, why things are such an ambiguous? Why things are not certain? Okay, so that is what people started asking. Now, answer to this was actually given by de Broglie. In fact, what he said is, okay, if the electron is so tiny, by the way, electron is so tiny, in fact tiny, if it moves with a close to velocity of the light or any velocity, electron can move with a very good velocity. If things are certain level, they are going to show, remember, they are going to show, okay, a quantum particles, okay, quantum particles with mass m and velocity v, okay, they may show, right, the behavior like waves. Okay, I'll come to that. What is the behavior like waves is? If I go and if you just say lake, in the lake, you just drop a stone, you are creating a waves. Now the question I would ask is where the wave is located. Usually we think that wave is located at the point where it is like a stone is interacting or impacting. Of course not. The wave is located everywhere. So wave is something exists everywhere, from the disturbance to every point it exists. So the electron or a quantum particle with some mass is shows their presence. Remember, they show their presence or their behavior, their existence everywhere around them. Okay, everywhere around them. It is just like Sri Krishna said, I am there everywhere. Right? It's like Narsimha. Before Narsimha avatar, right? He has to exist everywhere. So likewise, the electron is existing everywhere. So why it is existing everywhere? Because of it shows some kind of a wave behavior. Wave behavior means it exists everywhere. Something like wave behavior means it has a wavelength. Okay. So wavelength, what is the wavelength? What is the number corresponding to that wavelength? So de Broglie gave a very good equation. He gave Planck's constant divided by mass and velocity of that particle is going to give you a wavelength associated with that waves. Okay. So remember, the mass of the particle is very small. It's a quantum in nature. Then only we will see that wave nature. In fact, the Planck's constant number dimension, like size is 10 to the power of minus 34. If the electron mass is 10 to the power of minus 34 kilogram per kilogram, and it can move with a velocity of 10 to the power of 8 meter per second. If you see, this is going to give you angstrom wavelength. Okay, so 10 to the power of minus 10 meters, which is a measurable wavelength for you. If I go for a smaller particle, let's say very larger particle, like a larger particle in the sense larger entities, like say a cricket ball. Okay, so the wavelength is going to be 10 to the power of minus 25 meters. So small, there is no wave nature as such. In fact, wave nature is there, wavelength is there, but I can't measure it. So if you go for a bullet, traveling bullet, the wavelength is probably around 10 to the power of minus 20 meters. It is there, but still it is immeasurable. So when it comes to electron, the wavelength comes out to be 10 to the power of minus 10. Amazing, it is a measurable optical range. Okay, so the electrons behaves like a wave because they're so tiny. Because of that, there is a wave nature we can associate for the electron present in the orbit also. That is what I showed you, wave traveling around particular orbit. Okay, right? So if I just have a thread, okay, there is a thread tied from two ends, you create a disturbance, it travels and then hits and then comes back and creates some kind of a standing wave pattern. Right? Disturbance is traveling, but it appears like a standing wave pattern. Right? So that is what I see or I can associate. Remember, it's not a wave nature. It is not an actual wave. It is some kind of a wave behavior shown by the electron in a particular orbit. Remember, not only in a particular orbit, it exists everywhere, right? So for every orbit, I can associate a particular wavelength. Okay, not just a particular wavelength. We can associate the number of wavelengths confined in a particular orbit. So the exactly center, like the orbit which is close to the nucleus, there may be only one wavelength is confined. The very far, little bit far, two wavelengths can be confined, and three wavelengths can be confined. Larger number of wavelengths can be confined. Okay. Hello. Please, Senthilji, please mute yourself. Or yeah, thank you. Yeah. So the wavelengths are the ones which is going to tell me about a particular orbit. Means the lowest orbit which is very close to the nucleus, I may have only one wavelength confined in that orbit. That is what you see on the right side, as if the wave orbits, electron orbits are like a tapes around the nucleus. In each tape there is a particular wave exists with particular number of wavelengths confined into it. Okay, so with this I can say, because of the wave nature showed by the quantum particle, their presence is existing everywhere. Can we use that idea to realize the quantum memory? Okay, now how the existence of electron is everywhere is substantiated or justified is explained in terms of mathematical model of a wave nature. Okay, so wave nature for me is like a wave traveling. It's like a sinusoidal wave. So mathematically, it's just like a mathematical sign function. We call it as a wave function. Okay, a wave function is there for a particular electron. You take absolute square of that wave function, you would be getting some hills, positive hills. Wherever there is hill is there, maximum is there, that is the location of maximum probabilistic location of the electron. Very good. Wherever there is an electron, there is a hill or there is a trough. Okay, crest and trough for a wave is there. Na? Wherever the wave is hitting at a 0 point, okay, in the disturbance, that is where electron is not going to exist at all. So there is a zero probability of electron existing there. Okay. Similarly, if the wave is like 1.5 wavelength is confined in a particular orbit, if one wavelength is confined in a particular orbit, I'll have energy associated with that particular orbit. That is how electrons are existing in multiple locations. Even when there is only one electron, it can have a possibility to exist in half a wavelength orbit or one wavelength orbit or 1.5 wavelength orbit. Now, how do I find where is the location of the electron? I just take absolute square of that wave function. Where there is a maximum, I'll say there is a probability. Okay. Where there is a minimum, there is no probability of electron existing there. So, for an electron, when I supply energy, when I go back and see, it can absorb or may not absorb means it is because of the wave nature. It may exist at one point and may not exist at that point. It exists at multiple points. So what we can do, we can confine the electron to exist in only two locations. Okay, somehow we can force that systematically. Experimentally, it is proven. Theoretically, is also possible. You can create a locations where electron can only exist in two locations. The classical, simplest classical analog is, okay, so in a room, right, there are only two chairs. If a person is asked to go and sit in a chair, he will go and sit in any one of the chairs, right? And which chair we don't know until we go and see. If there are 100 chairs are there in the room, if I ask the student to go and sit, he will check any one of the 100 chairs. Likewise, I remove all the 98 chairs and only keep two chairs and create location for electron to sit in two locations. Any one of the location, he will sit. And if I perform the experiment like several hundred times, I see like 50 times he sat in one chair, another 50 times in another chair. Okay. So mathematically, you can represent the dynamics of the electron using just like a Newton's second law, right? F is equal to ma, which tells me if there is a force acted on an object of mass m, it generates an acceleration a, right? So similarly, if the electron is put in a particular potential, means certain surrounding, a neighborhood, it is behaved by the effect of the neighborhood. It shows the wave nature of a wave function psi. How that wave function changes in space is actually described by the second order derivative in space, okay, plus a quantity of potential, okay, around the neighborhood potential multiplied by the wave function is equal to the wave function actually multiplied by energy with which the electron can exist in that particular wave function. So basically it is actually eigenvalue equation where H is a matrix of H is a matrix and E is the eigenvalue of that matrix and wave function psi is the eigenvectors of a matrix. Okay, so those two mathematically who are having eigenvalues, eigenvector, they understand what is this eigenvalue equation I wrote, where H is a Hamiltonian. Hamiltonian takes the description or gives a description of the system around the what we are considered. Let's say electron I am considering. Electron is surrounded by some neighborhood, other atoms or other let's say lattice. So those things are actually considered in U through H. Okay, H is actually having a combination of this first or second order derivative, spatial derivative, and U in it. In fact, H is equivalent to, in a classical way, it is equivalent to kinetic energy plus potential energy. Okay, that is a Hamiltonian
Sir,
for you. Yeah.
sir,
Yes,
sorry
ma'am.
for the interruption. Sir, shall we take 5 minutes break, sir?
Yes, ma'am. We can definitely take a break. Okay, so now it's 11:15. I'll conclude, and then we'll just get back. So,
Okay.
so using solving this differential second order differential equation, you would be getting a sinusoidal function. That is what plotted here. So from that absolute square of the sinusoidal wave function, you will get a probabilistic locations. Okay. So if you plot for 3 dimension, you will get orbits of an atom, right? That is what the hydrogen atoms orbit, several orbits you see, nice orbits you see, right? In fact, Heisenberg gave uncertainty principle saying that there are so many points around a particular nucleus, right? Okay, if you want to find the force, like a speed of an electron and its position exactly, you will not be able to find because they're so tiny, you'll always make a mistake. That mistake is actually showed in terms of errors in position and momentum, which is always greater than Planck's constant. Okay, so that is the impact or implication of this wave nature. Now, using that wave nature or using that ambiguousness, people started realizing a quantum memory. We'll take a 5 minutes break, and then we will restart how this quantum memory is going to be realized with this dual nature of the particles. Okay, fine.
Students, participants, questions posted in the chat box.
Yeah, please post the questions. If you have anything, I'll answer. Yeah, I think we can restart. We have another 40 minutes time. Okay, so 40 minutes, 30 minutes. In the last 10 minutes, we'll have a discussion. I would plan in that way. Okay, right. So as you can see, right, as you can see, the quantum memory is based on this ambiguous nature of the electron being in multiple locations at a given time. So I can enforce the electron to only exist in 2 locations. What are the 2 locations? This time I will choose the electron to exist in only 2 of the orbits. Which orbits? Probably n equal to 2 and n equal to 3. So if I just take this the inside of that part and plot it on the right, I'll have 2-state system. Okay, it is called 2-level atomic system. Remember, in fact, atom has so many levels. Only I am choosing 2 levels out of it and confining only 2 levels for the electron to exist, just like the example I gave you earlier. Like anybody who allowed to sit in a classroom, there are only 2 chairs. Only 2 chairs they will sit. So that's such a situation I can create experimentally. How do I create? The way I am presenting only 2 chairs at 2 locations, I can ensure that the electron to exist in 2 locations by supplying the photon of energy which suits exactly between 2 orbits, the energy separation. In that way, I only choose the electron to exist in 2 orbits. That is the catch, right? How much supply energy I give, that is only going to decide electron to exist at the level 2 or level 3. Okay, right? So, and moreover, if I supply the energy to this atom or an electron, there is a chance it exists in a ground state with 40 times. There is a chance of 60 times in a probability. There are numbers involved here. What numbers? The probabilities are involved. Can we use that probabilities to realize the memory out of it? Okay, so that is how the quantum memory of 2 bits is realized on a single atom. Remember, on a single atom, 2 probabilities are going to be saved. So that is what a quantum bit for you. The lowest information storage location is a single atom storing 2 probability numbers. 2 probability numbers is actually a quantum bit for you. Okay, so in short, they call it as a quantum qubit. So in Shor's algorithm earlier said 10,000 number of qubits are required. So 10,000 such qubits are required to implement Shor's algorithm. Remember, atoms are so fragile. They get influenced or affected by the surrounding temperature. Why is that so fragile? The amount of energy required for electron to go out of this level 3 to any other outermost orbit or just completely knock out of the atom. So to go there, it needs some energy. Interestingly, there is a surrounding ambient temperature, whatever is there. That temperature itself can able to give the energy to the electron to just completely jump out of the electron atom. So we don't want that to happen. That's why we confine the atom within a certain temperature by cooling it. That is where this defreezing, this huge defreeze setup is actually involved in quantum computers. Okay, so now we know what is a qubit. Qubit is the short form for quantum bit, which stores two informations or two probabilities in that. Okay, now fine, we want to process the information. How do I process the information? Question is, first of all, I have to represent mathematically and see how mathematically information can be processed. From there, I can build the quantum memory processing. Okay, fine. So just now we are talking the electron being existing in multiple locations because of its wave behavior. Now, can we put that into the form of some mathematical equation? Okay, right? So let's say we will put a wave function psi of a quantum system or atomic state of an electron is equal to 40% of not excited, 60% of excited. Why did I add is 100% I should get because within there is a location within the room. The person can exist in multiple locations means the person exists inside the room with 100%. Where he exists, that is a thing we have to find out. So 40% in one location, 60% in another location. That is fine. Overall is 100. So let me say if I write the wave function in this way, does it make any sense? Of course, no. Why? Because wave function for me what? It's like a sinusoidal wave. So a sinusoidal wave, and you take absolute square of that wave, you get a hills. Where there is a maximum hill peak is there, electron should locate maximally at that point. Where there is a hill is hitting minimum point, no electron. But the thing I see here, the wave function representation I give mathematically is actually not giving that kind of an impression. That kind of a conclusion we are not able to draw. So what we'll do, let's slightly change using the Paul Dirac's idea. Actually, Dirac came up with this notation. He said, I will write the wave function just like a equation of a two-dimensional vector. What is that vector is? Vector in a Cartesian coordinate system will write r equal to xi plus yj. And he said, like he mentioned, I and j are the unit basis vectors on which the two-dimensional vector is defined. Okay, can I do that? Like he said, he thought that can I write the wave function into this kind of a notation? What is that notation is? He introduced the base vectors, just like I and j unit vector. He introduced the base vector as ket excited and ket not excited. What is this ket is? He took the word bracket, divided into parts. The right half is he called a ket, and the left half he called a bray, and there is a C. He reserved that for something called quantum mechanical operators. Okay, right? Hamiltonian we just saw earlier is a quantum mechanical operator. So C is reserved for that. Now we will come to that sometime later. Right now, so ket is a straight line with a right angle. If you write, it's called a ket. Whatever is there inside, it's called a psi ket. The Greek letter psi is there. I have a psi ket, which is just like a two-dimensional vector for me, like r vector. Okay, and ket excited is just like a j unit vector. Ket not excited is just like a unit vector I. Right? Now he introduced this where there is a alpha beta are actually the probability amplitudes he called. He did not say the alpha and beta are probabilities. He called it as a probability amplitude. Actual probabilities you will get if you just take a square of them, absolute square of them, you will be getting probabilities. If you introduce such kind of a notation, then if you just take a quantum vector, okay, now right, I'll write a classical analog on the right, classical analog, which is r equal to xi plus yj. Okay, on the left I have a quantum version, quantum vector, which is quantum state psi ket is equal to alpha. This time instead of writing not excited, excited, I'll just call it 0 and 1. There are only two possibilities. Let me call not excited as 0 and excited as a 1. Okay. Now if you see, there is a very good resemblance between each other for on paper. But the thing mathematically also there should be a resemblance. What is that resemblance is? I vector and j vector there is a base. Okay, Cartesian coordinate system basis. Here 0 ket and 1 ket is a basis. For time being, we don't know what is this basis. Here we may see the dot product between the unit vectors is 1. Dot product between I and j is 0. So j with the j is 1. That we know it's the cross product. Sorry, it's a dot product which defines the I and j and their operations and their existence. That they're giving the dimension, the description of a two-dimensional vector. So here question is, what is the operation between? The question is, okay. The question is, what is the operation between the base vectors, unit vectors 0, ket and y? And if at all there is a very good resemblance, a very good analogousy between quantum vector and the two-dimensional vector, means 0 ket and 1 ket also we should behave like a I cap and j cap, right? So for that, Dirac introduced a matrix interpretation. What is that matrix interpretation is? He called a 0 ket as a column vector 1 0. He called a 1 ket as column vector 0 and 1. Now the operation between 0 to 1, he called it as, or he introduced, left hand side I will take a transpose of it, the left hand side, and multiply it to the right hand side, which is going to be, let me correct here, okay, right, which is going to be the ket of 0 becomes, the right angle becomes a left angle. I'll have a braid. He call it as a 0 ket transpose is actually a braid. A ket transpose is a braid. Okay, so he introduced that. So here, if you see in a matrix notation, the column vector is of 2 by 1 dimension. When I take a transpose of it, it becomes a row which is 1 by 2 of dimension, right? So in that way, I can have a matrix multiplication between 0 ket to 1 ket as like this. Okay. Now you see the matrix multiplication is giving you 0 in 1 into 1. Sorry, I'm sorry. I made a mistake again here. Okay. 0 and 1. 1 into 0 plus 0 into 1 is going to give me 0. So there's an operation between 0 to 1 giving me 0. It is just like equivalent to I dot j giving 0. Now, if you find out the operation between 0 to 0 is going to give you, in fact, 1. Beautifully, you will get I dot I is just close to, like the way I dot I giving 1, the same way operation between 0 ket to 0 gives you 1. Similarly, 1 ket to 1 ket gives you 1. Okay, they call it this operation as inner product. Okay, so in short form, they'll write inner product between any two elements as x inner product with y. Okay, so on the left you have a bray, on the right you have a cat, so altogether it becomes a bracket. Okay, C is missing. Let's say some Hamiltonian is there in between. Okay, quantum state psi is there, so there is a bracket is all the way realized, even pictorially or alphabetically. Okay, so the moment you introduce this kind of a matrix interpretation, everything falls into the picture. Even quantum vector behaves just like a two-dimensional vector, xi plus yj, where x and y are the components which tells me how much strength R is having along the x, means how well R is flowing along the I direction, how well it is flowing along the z direction is given by y. Okay. Similarly, alpha and beta would tell me whether the system is in the ground state or in the excited state is actually conveyed. Alpha absolute square would give me the strength or the probability with the electron can exist in the ground, and so on. So the quantum states are going to form a space, a vector space called Hilbert space, where the inner product is an operation. Okay, and the moment you bring the inner product operation, even the quantum state is also represented by a column vector alpha beta, and its transpose is a bray, it becomes a row vector. Okay, this is a column vector. Fine. So with this, even mathematically also it becomes very simple. What you can do, the way two-dimensional vector is having a geometrical interpretation, you see, it's like a unit vector here, you see. So x and y is actually confined to have a certain value. X square plus y square is equal to 1 means I'm only talking about points on the unit circle. Okay, so it's like a unit circle. So why I put that condition, because for me alpha square and beta square also should be 1. Their sum should be 1. To have such a correlation between the two-dimensional Cartesian coordinate system vector and a quantum state vector, I impose that condition and will have a points on the unit circle. That is how geometrically the points on the unit circle is described here. Now the question is there a geometrical interpretation for a quantum state? Yes, there is. What you do is you introduce alpha is equal to cos theta by 2 and beta is equal to exponential I phi sin theta by 2 conversion. In that case, if you just take a three-dimensional spherical coordinate system, so three-dimensional 3D spherical coordinate system, if you just take coordinate system, okay, if you take, there is a r vector, there is a theta vector, there is a phi vector. R is a distance from the center, okay, from a point, and theta is a polar angle. Okay, any vector makes a angle theta with a north pole, and phi is an angle the shadow of that vector makes in the equatorial plane. It is also called azimuthal angle. So just like we have in Cartesian coordinate system, I vector, j vector and k vector, in a spherical coordinate system we'll have 3 unit vectors, r cap, theta cap and phi cap. Now if you introduce the theta and phi into the alpha beta with this expression, what happens? Any point on the spherical surface would represent the quantum state. How? I just ignore r, I will just fix r equal to 1 unit radius. In that way, what happens? I'll have point on the spherical surface as a potential means to describe a given quantum state. Now, specific cases, if you just see, if you just take a theta equal to 0, in that case, what happens? Cos 0 is 1, cos 0 is 1, sin 0 is 0. So I'll not have any quantum state contribution coming from second 1 ket, only contribution from the 0 ket. So the north pole is actually a 0 ket. Okay, if you just take a theta equal to pi, okay, in that case sin pi by 2 is 1, cos pi by 2 is 0,
The south pole is actually gives you a quantum state 1 ket. Okay, so any other point, if you just take theta and pi values would exist, so those values would contribute for a quantum state. We will have a superposition of 0 ket and 1 ket in the contribution. That is what you see along the x-axis. You see 0 ket and 1 ket contributes equally, because theta by 2 would be 45 degrees. Okay, and cos 45 would give you 1 by square root of 2, sin 45 would give you 1 by square root of 2, and phi is a 0 with 0 along the x-axis. Okay, phi is an angle made with an x-axis. Along the x-axis phi is 0, so what I'll have exponential I phi is 1, so I'll have equal contribution with a 0 ket and 1 ket along the x-axis I'll get. So it is called a plus ket in a quantum state representation. Along the y, if you just see, there is a phi angle actually contributing about pi by 2 angle. Okay, so phi is equal to pi by 2 means I'll get a complex iota for the contribution for the I vector. That is what you see. This is called plus I ket. Okay, so along the negative x direction, you will have a minus I ket. There is a minus sign comes here. Okay, so this is how geometrically you can represent a quantum system. Very good. Now, 1 qubit is allowing me to store 2 bits of information, right? How do I store 2 bits of information, sorry, 4 bits of information? I'm not satisfied with just 2 bits. How do I generate a large number of information storage? So, to start with, what you can do is just to take 2 atoms, atom A and atom B. Okay, you put it in a box, atom A and atom B. Now they interact, they evolve into a new quantum states. Okay, so basically it's just like take 2 coins and toss them. To toss 2 coins, one coin can fall in head, another coin can fall in head, another coin can fall in tail. So there will be 4 chances. What are the chances? 2 coins giving you 4 possibilities for you: head head, head tail, tail head, tail tail. So likewise, if you just take 2 quantum coins like atoms of 2 possible states, one atom in the ground, another atom in the ground, 0 0 ket, 0 1 ket, 1 0 ket, 1 1 ket. So what I mean is, the first entry stands for first atom in the ground, second entry stands for second atom in the ground in the first case. Likewise, you can realize 4 memory locations using 2 atoms. How? I'll have the probability amplitude associated with each atom. Okay, when I combine them, mathematically I can represent that such a combining in terms of tensor product. Okay, the moment you use a tensor product, basically you are just showing 2 atoms are about to interact. When they interact, they may exist in 4 possible ways. So that is corresponded by a probability amplitude of alpha 0 0, which is actually equal to probability of alpha A and alpha B. Similarly, other probabilities. So in short, I'll write alpha 0 0. So the 4 possible chances of memory locations were realized. This is just like using 2 atoms, or you're going to create 4 possible memories. Okay, so in short, you are actually creating a new basis. Earlier I have a 0 ket and 1 basis, right? Now we have 2 atoms, so you'll have corresponding to A you'll have 1, corresponding to B you have 1 more basis. So you combine them, you are going to create a basis of 4 states. Okay, 0 1, 1 0, 1 1. Remember, first entry is atom A, second entry is atom B. Okay, so you can write in that way. So this is how you are going to generate a new basis of higher dimension. Okay, so the dimension size of the basis is 4 here. You cannot stop at this point. You can keep going. You can have higher dimensional quantum systems. Remember, what is the representation for 0 0? It is the tensor product between 1 0 1 0 columns. It is going to generate the tensor product, generate 4 by 1 dimension vector. Okay, so how you know the tensor product operation is showed here. Take the first element, multiply to both the elements. Take the second element, multiply to both the elements. You are going to get the tensor product in there in that way. So called Kronecker delta. Okay, so higher dimensional quantum system or higher dimensional memory is realized just by adding the atom together, and you are going to generate. You can go crazy. You can generalize for some n dimension system, 2 to the power of n dimension system. You just take n qubits, which is going to generate 2 to the power of n bit memory locations. So you are going to have higher dimensional storage. Okay, very good. Now I know the information storage. How do I create the processing out of it? Okay, so as we know in a classical computing, there is a processor of information. Is, let's say I send a high information through a signal. Let's say I send a 0, it becomes 1. I send 1, it becomes 0. Now the question is there such a negation gate is there in quantum computing to process the information? Of course there is. What is that is actually called a NOT gate operation. Okay, right? Let's say I have a superposition state, a quantum superposition state. Now I will call it a superposition state for a quantum vector, where the atom can be in the ground, atom can be in the excited with corresponding probability amplitudes. Now, in that case, if I send such information through, what happens? 0 becomes 1, 1 becomes 0. That we know. The quantum information gets flipped. Okay, if there is any NOT gate. Now the question is, if you observe a new state which is obtained out of this quantum gate, let me call it as some psi prime. Okay, if you notice, compared to the previous quantum state psi, what happened is 0 ket and 1 ket remaining intact, but the probabilities amplitude actually swapped. Okay, the probability amplitude corresponding to 0 went to 1, probability amplitude corresponding to 1 went to 0. So that is the swapping operation taken place in the probabilities with a NOT gate operation. Okay, so you can see a column representation for a quantum state psi is alpha beta. Column state representation for a psi prime is beta alpha. Now the alpha beta becoming beta alpha means some kind of a matrix transformation might have been taken place. So by guessing trial and error method, you can guess what would be the matrix operation required for having such an effect is actually 0110. People call it as an X gate, X quantum gate. Now, interestingly, alpha square plus beta square remains the same on the left side. Alpha square plus beta square remaining on the right also. So the length of the quantum state remaining the unit vector. So you say quantum like a norm of quantum state is reserved here. So the operation which we are seeing here, the X gate operation, is not any X gate. There should be a specific X gate which does that. What is that is, this quantum gates has to be something called unitary in nature. What I mean by unitary in nature is, if I just take a unitary gate acting on psi, use your psi prime means you take an inner product on the left and right between each other. Okay, so the length, like it should remain the same. The length should be remaining same. What is the inner product between left? Inner product between left is unitary acting on the unitary. So this is the unitary product. On the right, I have a inner product between psi prime to psi prime. So this is what promised. Okay. So inner product means left hand side become a transpose of it. Unitary becomes U transpose. This time I'll write a dagger. And right is as it is. On the right I have psi prime to psi prime. Now you see, the right hand side is the length of the vector, which is 1. Left hand side is also length of the vector, which is 1. Remember, when is that possible? U into U dagger is actually identity matrix. Then only it is possible. That's why all the quantum gates are actually called unitary gates by nature. If there is a unitary matrix is there, I can realize a quantum gate out of it. Okay, it is a one-to-one relation. Now, Apart from negation gate, what effect I can have a quantum state? Another effect I can have on a quantum state is there is a relative phase between probability amplitudes alpha and beta, means both are positive. I can induce a negative phase, I can induce a negative sign between alpha and beta by some gate operation where psi going through some gate picks a negative sign for a beta. So that is called a relative phase is introduced between 0 ket and 1 ket. How it is possible? I can try and guess what is that Z matrix would be. It is 1, 0 and 0 minus 1. Now, if you just find what is the Z dagger with a Z, in fact, it is identity. That means Z is a unitary gate for sure. Okay, right? And one more thing, the important gate in quantum information processing is called Hadamard gate. What is this gate? Let me use my hand note and quickly explain. Okay, so people do use Hadamard gate representation with a H, Hamiltonian also with H. To represent a small difference, you can put a hat over the Hamiltonian. Now let's come back to the Hadamard gate. Hadamard gate. What is this gate does is, if the electron is strictly in the ground, okay, it pushes the electron to become a superposition. So initial, let's say quantum state is in the ground state. If you act a Hadamard gate on that ground state, it puts that into superposition. What superposition? Equal superposition. Means 50 times electron can exist in the ground, 50 times it exists in the excited state. That is what happens when I act a Hadamard gate. Means electron hops into the excited state and then comes back to the ground state. Why? It has a lifetime of 1 microsecond. Any electron cannot exist in the excited state forever. After 1 microsecond, it comes and emits that photon. Now what I'll do? Initially, I supplied a photon. It comes out after 1 microsecond. I'll place one more photon exactly after 1 microsecond apart. In that way, what I do? I can make the electron to hop between ground to excited continuously, as if something like a fan is rotating, wings are rotating, so electrons are rotating. So how do I create? I send a pulse of photon which is having an area of pi by 2. Okay, so this is called a pi by 2 pulse which is having so many photons which are placed rightly. So this photons would put the electron in the superposition state. That is what the equal superposition here. So this is what the Hadamard action in the lab. Hadamard action in the lab is supply of a photon pulse. Supply of photons. Okay, right? So quantum mechanical, if I want to write, or mathematical, if I want to write, the Hadamard gate would be 1 by square root of 2, 1, 1 minus 1. In fact, it is a X gate plus a Z gate with a 1 by square root of 2. Okay, it's like acting both the gates, right? It's not that straightforward. It is actually mathematically like that. Okay, Hadamard gate is like that. Okay, fine. Let's get back. We are reaching at the end, so I'll just quickly go through the remaining part and conclude. Okay, so Hadamard gate, exactly, again you can cross check. It is a Hadamard gate, and in fact Hadamard gate is pushing the electron from one state to superposition state. So basically quantum gate operations are just like rotation about some axis. So any quantum gate, if you just take rotating of a quantum state from one direction to other gates. Okay, there is another important quantum gate is called a C0 gate. It takes two inputs. One is control, another one is target. Whenever his control is high, then only target becomes flipped. It is just like a X gate acting on the target depending on the control. So X gate representation is represented with addition modulo because it is just like addition modulo operation, right? So you add 1 to 0, you'll get 1. You add 1 to 1, again you'll get 0. So it's like flipping, 0 becoming 1, 1 becoming 0. When I add 1 to those inputs, so addition modulo operation is actually involved in X gate operation. So controlled X gate is controlled addition modulo operation. If you write the truth table, it would look like this. Usually people don't write truth table for quantum gates, but for C0 gate you can write. So there is a two controls. There is a target output. You don't bother about the control in output because it is coming as it is. Okay, a C0 gate is something which changes the state of the target depending on the control input. So this is a matrix representation. You can even guess now. A C0 gate is taking two inputs, means the dimension of the input is 4 by 1. You see, so the matrix required to represent that is 4 by 4 matrix. Wait a minute, 4 by 4 matrix. So a C0 operating on a different quantum 2 qubit system gives you different output. You can cross check and see that later. Okay, so these are like quantum gates. One interesting thing about quantum gates is they're reversible in nature. What I mean is, if you just take any classical computing gates, they're creating output at the cost of destroying the inputs. Okay, so there is no way you can get back the information in a traveling in a reverse fashion. So irreversibility is there, but in quantum computing, the reversibility is there. What I mean is, you act a quantum state twice, quantum gate twice on a same quantum state, I'll get back to the same state. Like you can drop back the quantum state or a get back quantum state by acting quantum gate twice. Okay, right? So that is very, very important. The reversibility of quantum gates is always allows me to debug the initial information from there. Okay, right? So now you can combine the quantum gates and you can get a beautiful effect, something called entanglement. You take a Hadamard gate, you take a C0 gate together and start with both the quantum qubits or both atoms in the ground state, ideally, and you can create a entangled state. What is this entangled state is? This superposition exists between 0, 0 and 1, 1 is equal. Okay, which means if I do something with an atom A, something else also will happen with atom A, irrespective of something is nobody has fiddled with atom B. Okay, so entanglement in a real world you can understand, like if you have two people, right, two strangers, combine them into one room, right, after the interaction you separate them, let's say they become a very good friends. You hit one guy, even the other guy is not in the vicinity, the other guy also feels the pain. So it is something which we don't understand or don't accept to understand or agree. So same happened with Einstein also. He disagreed with this kind of entanglement effect. Okay, why is this effect exists? Because nature has given such an ability for the quantum systems to interact and create their some kind of a mutual state of this entangled state. Even when they're separated, the mutual state effect exists on them, like a telepathic effect exists on them. Even when they're separated, their fate is actually decided by action on any one of them. Okay, right? So we'll come to the details later probably. And using quantum gates, we can have variants of different effects. There is something called quantum swap operation you can make. Quantum states can be swapped between the quantum registers, and you can have controlled unitary gates. Okay, so even you can realize the classical gate operations like and NOR, and NAND operations you can realize about quantum gates. There is something called Toffoli gate, means two controls and one target. Okay, there is a replication you can do. Remember, only single bit replication possible, but you can't replicate a superposition state. Okay, a superposition state cannot be replicated because quantum states are so fragile, you can't replicate. One thing you can do, you can destroy at one point, you can create another point. That is like conservation of quantum states. Okay, so mathematically you can show why cloning is not possible or replication is not possible from a contradictory proof by contradiction. Okay, so now the question is, not only electron being around the nucleus would be a potential candidate for me to realize a qubit, there are other means, like electron itself is rotating about itself. It has a spin, magnetic spin. Similarly, nuclear has a nuclear spin. Interestingly, if you try to find what is a spin, at a given point it will be up spin, at a given point it will be down That is also probabilistic in nature, like a wave nature, like 60% is up spin, 40% down spin. That is allows me to store 2 bits of information. It is a quantum bit out of spin. Okay, so that is how electron spin or a nuclear spin is used to realize a qubit out of it. So there are other means like optical cavity, means you take a photon, put it inside a cavity like two mirrors. Okay, how many times it goes through several oscillation and exits. Okay, what is the frequency which it exits? That is also becomes a quantum in nature, means it is ambiguous in nature. Depending on, you can realize a qubit out of it. And not only that, if I just take an electromagnetic wave, the photon has a polarization. At a given point, it can have particular polarization, horizontal, sorry, vertical or horizontal. Sometimes it becomes superposition, means it has a combination of both horizontal and vertical. In that way, a qubit can be realized out of a photon. Okay, so there are so many other ways you can realize a qubit. Now the question is how well you can process with each one. Okay, so processing in the sense how many operations you can realize. For each operation, how much time it takes. For example, there is operation time we have given, and how many, what is the lifetime of superposition time, means how well the system can exist in superposition state. Okay, how long it exists. Within that time, I have to make certain number of operations. If you just see number of operations possible with each kind of quantum qubits, there are certain number. So usually we tempted to see the one with a large number of operations, which is a very good means to realize a qubit and large number of operations. But it is not that straightforward. Okay, the number of operations doesn't mean it is highly controllable. So you should balance between the controllability as well as the number of operations. That's why people are using ion traps for realizing qubits, and even quantum dots people are using. There is something called rare earth ions also they'll use to realize a qubit out of it. Okay, so this is 4 ways of quantum qubit realization. So there is something called transmons, means using LCR circuits, electronic circuits you can realize. This is based on photon. This is ion trap. Okay, and the last one is called NV center, means remove the carbons from the diamond and you put a nitrogen and keep one vacant as well as it is, and you create a NV center. It becomes a qubit. It's very sensitive to external magnetic field, electric field. Using that, you can do a lot of processing, and you can use even for sensing. So this is a qubit realization in the lab. Okay, so what is how the transpond works? It is just a LCR circuit. You remove the inductor with a Josephson junction, which is a superconductor. In between there is an insulator. If you cool this superconductor to millikelvin, what happens? Cooper pairs are formed. Electrons becomes pairs, and they become so powerful they jump between left to right, and they oscillate with certain frequencies. Because of that certain frequencies, what happens? Capacitor gets charged in various charge ways. Let's say 10 coulomb, like 15, 17, and 19, like that. There is unequal separation of charge states of the capacitor. That is going to give you something very close to the real world natural atom. So that is how you can realize the qubit out of just a artificial atom. So this is called artificial atoms with the LCR circuit. It is also known after transmons. Okay, so there are so many applications out of quantum computing, right from medical applications for the drug discovery and cyber security with securing information, and you can use something called quantum key distribution to create a queue between two entities, secured key which nobody can create. So in that way, you can use quantum computing for various applications. So there is, again, in a similar direction, you can start using for research opportunities, quantum materials, that is a material study, just like drug discovery and so on. So the players, as you guys know, IBM, Google, so many big giants are there. D-Wave from Canada is there. Okay, Alibaba Group from China is there. IonQ and Microsoft is anyway there. And Xanadu Photonic Systems, HP, all are there with the existing corporate worlds working in a quantum computing. Okay, So I'll just stop at this point and then conclude and then seek some questions if there is any. So we started with the number one, why and how and quantum computing has started. It is comes with the trigger or a spark from Richard Feynman, and how qubits are realized, okay, and how they are processed, okay, how processing with the gates, okay, combination of gates giving effect of entanglement, okay, that is like quantum circuits, and right, and how to realizing qubits, okay, hardware wise. Those are the things which we discussed, and probably in the next session we would start on quantum algorithms. Basically, it's a combination of many quantum circuits giving us some interesting effects which are useful for real world tasks. That is what we will do it in a tomorrow session. Okay, right? So if you have any questions, please do ask now or put up in a chat message. If you are allowed to unmute, please unmute and ask. I would be happy to answer. So those who are already attended MNIT Jaipur FDP, I hope for them it is not boring. It is in a way kind of a revision. Okay.
Participants, is there any queries? Please ask.
50 plus people are there. Or if you have no questions right now, later if you have anything related to research or anything, you are welcome to write to me or reach out to me. My phone number and email ID is with organizers. You can take from them, right? You can reach out to me or write to me. I would be happy to answer them and get in touch with you, and we can do collaborative work together and write some proposals or anything in future. Okay, so that is also possible. Okay, there is a message. Please share the PPT. Yeah, of course. Yeah, Dr. Karun. I'll definitely share the PPT with the organizers. Okay. Yeah. Thank you, Nitya ji, for your encouraging words. Yeah. Right. So thank you so much, participants, for listening to me for continuously 2 hours almost. Right. And once again, I thank the organizers for a very good opportunity for me to introduce this quantum computing. We build on this for tomorrow, quantum algorithms, right? And we'll see interesting quantum error correction as a part of my third session, which is on coming Monday. Okay. So tomorrow we will be touching quantum algorithms. If you have any specific things to ask tomorrow, you can list it out as a points and ask me tomorrow. I would be happy to answer any question in entire quantum computing. Okay. So nothing like I'm not confining myself to only algorithms for tomorrow. You have any specific questions to ask, you are welcome to ask. Okay. Right. Thank you, Suhana ji, for your kind encouraging words on this session and feedback wise. Okay. Okay, ma'am. Over to the organizers. Thank you very much. See you tomorrow.
So if you have any queries, you can confirm it with sir.
Yes.
A heartfelt thanks to Dr. H. Aswath Babu sir for an inspiring and enlightening session on quantum computing. Today we were not only merely listeners, we were explorers taken on a journey through the history of quantum computing, introduction to fascinating fundamentals, and given a clear view of how quantum computing stands apart from classical computing. Your insightful explanation of quantum algorithms, the RSA algorithm, and the legends of single and multi-qubit gates has not only deepened our understanding but also sparked our imagination. The way you connected complex ideas with clarity and enthusiasm made the session truly engaging and thought provoking. We are immensely grateful for your time, knowledge, and the inspiration you have shared with us. Thank you for planting seeds of curiosity that will encourage us to explore this revolutionary field further. A special thanks to all participants for making this faculty development program a memorable and enriching experience. Thank you, sir.
Thank you very much once again. Have a nice day, all of you. See you tomorrow. Bye bye.
Thank you, sir.